Morning. There we go. It's working now. All kinds of folks joining in. Hey, good morning, everybody. It's what's today? Today's Thursday, April 22nd, 2021. And it is now a minute after 11 o'clock. I'm running a little bit late. That's okay. We our digestive system, I think we're going to try to finish that up today, maybe. And then next week is your last week, and hopefully do reproductive then. Maybe we'll get to it today. I'm not sure. I think last time, how far did we get? Do you remember? The stomach. Just finished the stomach wall. Oh yeah. Okay. Yeah. And then we're going to these accessory digestive organs. That sounds about right. And so here we are. Let me. That's nice. Here we go. Fix it for the folks in here. Grab my laser, and there we go. The liver, the gallbladder, and the pancreas. Beginning with the liver. What is the liver? See the big old reddish brown mass right there? That's your liver. It's huge, huge gland, huge gland. I define it as a reddish brown gland located inferior to the diaphragm in the right hypochondriac and epigastric regions. Always, always, always tucked right up underneath the diaphragm right there. It's immediately like it's the first thing you find in the abdominal pelvic body cavity, the liver and the stomach, the side by side, but most of it's liver, right? The largest gland in the body performs a tremendous variety of functions, including the secretion of bile for digestive purposes. And that's what we're going to concentrate on for anatomical reasons. But when you get into physiology, you're going to learn about all kinds of stuff that the liver does. And we kind of talked about the liver already in passing when we were talking about blood vessels, particularly portal vessels. Remember the hepatic portal system, where you basically drain the gut, all this stuff down here, with a portal vessel that goes to the liver. Why does it do that? Remember I told you my analogy, where I said your liver is like your body's refinery, in the sense where your gut is the body's oil field. Where you get crude fuel from the oil field, you got to send it to the refinery to be refined for usable metabolites. So basically all the fuel from your body comes from the liver, your body's refinery. And it does all kinds of things. You know, it takes and gathers glucose and turns it into a storage form called a glycogen. And of course, that's what your body, all the cells of your body burns as fuel. And so it's a very, very large gland, large organ, doing a whole bunch of things. And like a refinery, boy, it generates some heat. Have you ever driven past a petrochemical refinery? And the heat of all those pipes and things that you see everywhere, smoke stacks and steam coming out, all the heat that's coming out of there, all the mechanisms that are happening. Same thing with your liver. It generates a lot of heat. And so really your core temperature, your 37 degrees centigrade or your 98.6 degrees Fahrenheit, comes from your body's furnace, and your body's furnace is your liver. It generates a lot of heat. Anyway, and another thing it does for digestion, breaking down of things, it manufactures bile, okay? And bile, we talk about the liver, the gallbladder, and the pancreas, you know, kind of all together like that. But the gallbladder we're going to see is really just a portion of the liver, but we kind of segment it out as an accessory digestive structure because it kind of seems like its own entity. But anyway, let's talk about the gross anatomy of the liver. So here it is by itself, anterior view, looking at it, you know, from the front. Typically, the gross anatomy includes 4 lobes. You have a a large right lobe and then a smaller left lobe, and the two are separated by this falciform ligament. Okay, and that falciform ligament is a portion of the body's mesentery. You have dorsal mesentery and ventral mesentery. This is part of the ventral mesentery, and it just kind of sections the liver in two. But if you flip the liver up underneath, you're going to see that the right lobe has 2 sublobes, a caudate lobe and a quadrate lobe. And we'll take a look at those. The falciform ligament, like I said, it separates the 2 lobes. And then you also have a noteworthy structure associated with the falciform ligament called the round ligament. And most books point this out because what is the round ligament? Well, here I tell you that the round ligament exists as an inferior extension of the falciform ligament. It is a remnant of the umbilical vein. Your umbilical vein, you know, what my umbilical vein? Well, when you were a fetus, you were connected to your mother's uterus by way of an umbilical cord. And in the umbilical cord, there are 3 blood vessels, a right and left umbilical artery and an unpaired umbilical vein. The umbilical arteries are branches of your, as a fetus, internal iliac arteries. Okay, and that was carrying blood from your body back to the placenta. Okay, in return from that, you have an umbilical vein from the placenta to you, and it's coming to, and it goes through the umbilical cord, through your belly button, and from the inside of your belly button, it travels up and to your liver. And there it is. Well, it's why they call it a round ligament. Well, you don't have an umbilical cord anymore. When you lose your umbilical cord, you lose those blood vessels, and those blood vessels just kind of shrivel up inside your body and exist as kind of like these thickened kind of ligaments. And so anyway, that's a kind of a long explanation to a short story for, you know, what is this? Well, that's what's left of your umbilical vein that kept you connected to your mother by way of the umbilical cord. Anyway, so here we're flipping up the liver. Here's the anterior aspect, posterior aspect. Here's the falciform ligament, or could be the round ligament is in there too. But anyway, you flipped it up and you can see the caudate lobe in the back. I tell you, the caudate lobe occurs between the inferior vena cava. That's what this is, the inferior vena cava, which is right there on the back body wall, and the falciform ligament. So this little wedge right here of the right lobe is identified as the caudate, with a C, caudate lobe. And then in the front, between the falciform ligament and the gallbladder, is the quadrate lobe with a Q, quadrate, okay? And of course, the gallbladder itself, it adheres to a depression in the inferior surface of the liver between the right and quadrate lobe. So it's identifying, you know, where you find the gallbladder, which again, it kind of seems like it's a separate organ. It kind of is, but it's an organ that belongs to the liver, okay? Another structure worth noting from this view, the inferior view of the liver, is the porta hepatis. The porta hepatis, porta means like small little port, like a port, you know, like where ships come in, ships go out. It's like things are happening in a port. Ports are busy, right? Of course, hepatis is of the liver. So literally the small port of the liver, or it's nicknamed the gateway of the liver. If you flip the liver up, it would look a lot like this. They're kind of smooth, no blood vessels or anything in these areas right here. It's just kind of a slick gland. But there's one spot right here that's completely enveloped with fascia and connective tissue that's wrapping up blood vessels and ducts associated with the gallbladder, and you can hardly see it. And so that's where everything's entering and exiting the liver. And that's this little region we call the porta hepatis. And in this diagram, you see the little white line that's with all the fascia just cut away, so you can see what's going on in there. So I define that porta hepatis is, on the inferior surface, it's the site of vessel and duct entry to and from the liver. So it's not really a thing, it's kind of like a place, a zone or an area of the liver where everything's coming in. You can see this little red vessel and this little blue vessel. That's all the blood to the liver, okay? That's the red one. The little red one is the hepatic artery, or the common hepatic artery. And the blue one next to it is the hepatic portal vein. Both are carrying blood to the liver. Remember that? 20% is from the artery, and then about 80%, like most of the blood supply to the liver, is by the hepatic portal. That's where everything's coming in. And then this green coming out, of course, that's going to be the bile that's coming from the gallbladder and or the liver itself on its way to the small intestine. And of course, all the blood is going to be drained way up here. You're going to have hepatic veins draining the liver into the inferior vena cava. Okay, so there's that. Now, that's gross anatomy. There's a microanatomy. Look at it up close, and you can see these little hexagons everywhere. And they're hollow. They're a little hollow center, these little hexagons. I guess that's a hexagon. Is hexagon a six-sided figure? Is that right? Yeah, she knows. Right? So, the microscopic anatomy. The liver parenchyma, the parenchyma, the functional part of the liver, consists mostly of hepatocytes. That's what you call a liver cell, a hepatocyte. They're arranged in these little cylinders, little hexagons, called hepatic lobules. So this is one hepatic lobule, and there's another one, there's another one, there's another one. They're about 1 millimeter in diameter, about 2 millimeters long. And of course, they have that hollow center, which is identified as the central vein that passes through its core there. The liver secretes bile into narrow channels, which are called bile caniculi. Well, I don't know if they're pointed out somewhere. Anyway, they're between the little sheets of hepatocytes, and the bile passes from the caniculi into small bile ductules encircling each lobule. So at the outer corner, so to speak, you have your little bile ductules adjacent to the blood vessels and so forth, all right? Once you have bile in the ductules, of course, then it's going to be drained out. So here I have the bile passage from the hepatic ductules. Bile exits the liver by the right and left hepatic ducts. And look at this. Here's your right lobe. Here's your left lobe. And you see the little branch coming over here from the left, and then the branch coming over here from the right. Those are the right and left hepatic ducts, okay? These two ducts converge. They come together to form a single common hepatic duct. So right there in the middle, with this one and this one come together, that forms the common hepatic duct. Get it? Okay, now what? Well, the common hepatic duct, the common bile duct, don't confuse common hepatic with common bile. The common bile duct, this one, the big long green one, that's the common, here they just call it bile duct, same thing, is formed from the union of the common hepatic duct and a duct from the gallbladder called the cystic duct, right here. Here's the gallbladder, and see the duct coming from the gallbladder. That's the, they don't label, oh, here it is, labeled right here. Well, it's hard to see. Cystic duct, right here. That one. So, you have 3 main ducts. A cystic duct, common hepatic duct, and common bile duct. Okay? Those are the 3 main ones. Okay? The common bile duct joins the pancreatic duct, obviously from the pancreas, right? Forming the hepatopancreatic ampulla. It spells it out for you there. Hepatopancreatic means liver and pancreas together, forming a little kind of an ampulla. It's like a swollen vessel, okay, with a distal sphincter. And of course, that sphincter is going to, it's a valve, right? It allows those secretions to enter into the duodenum. So you can see it open. This is the duodenum right here. And that allows for the passage of the bile and the pancreatic secretions into the duodenum. There you go. Advanced. There you go. So now we can talk about the pancreas. Here's your other organ here, the pancreas. I describe it as a soft, spongy gland dorsal to the greater curvature of the stomach and outside the peritoneal cavity. So it's retroperitoneal technically, right? It has both endocrine and exocrine functions. And then we talked about that way back when we were talking about different types of glands. We talked about endocrine glands, we talked about exocrine glands. Duct glands and ductless glands. Remember, exocrine glands were duct glands. And endocrine glands were ductless glands. But we said that there was one organ that was both. And there's only one example, and that's the pancreas. The pancreas is an endocrine exocrine gland because it has duct and ductless portions, all right? And I think I talk about that. The endocrine portion, which is, the ductless portion, consists of pancreatic islets. Some older books will use an eponym and call them the pancreatic islets, or islets of Langerhans. Yeah, I mean islets of Langerhans. I think pancreatic islets of Langerhans. Anyway, which means like little islands. If you look at it histologically, you got these little bitty patches of endocrine tissue embedded in there. And they produce what endocrine glands produce are hormones. And then the hormones that the pancreatic islets produce are insulin and glucagon, which collectively are to regulate your body's blood sugar, the glucose, for glucose metabolism. And all those pathways regulating this and how this does that and so on and so forth, that's all physiology. You'll get into that next semester. But that's the ductless portion, the endocrine portion, okay? But you can't really see. They're just kind of embedded in there. And then here, I tell you, most of the pancreas is exocrine, the duct part, all right, that produces a secretion that's delivered by a duct. And so the exocrine tissue secretes about 1,200 to 1,500 milliliters of pancreatic juice per day. And my goodness, what is pancreatic juice? That doesn't sound very appetizing, does it? Would you like a glass of pancreatic juice for breakfast? Anyway, this secretion ends up in the main pancreatic duct. That's the main one that's running the length of the pancreas, all right? It empties into the small intestine through the hepatopancreatic ampulla or by way of a smaller accessory pancreatic duct in some people. And I don't know if you can see, there's a little, yeah, there's accessory pancreatic duct. A little extra one that kind of branches off and opens up to the duodenum all by itself. Not everybody has that. Some people have this extra. Some people have two. Some of them have a superior pancreatic accessory duct, and some people have an inferior, or both. But it varies. But everybody has at least the main pancreatic duct, which is joined by the common bile duct, forming the hepatopancreatic ampulla. Okay, so what's the juice? Pancreatic juice is an alkaline mixture of water, enzymes, sodium bicarbonate, and other electrolytes. So it's a mixture of all kinds of things, and the different components and the different constituents do different things. Here I tell you that the acinar cells, or sometimes called the alveolar cells, basically the secretory portion of the glands, That's what produces the enzymes, whereas the ducts of the gland secrete sodium bicarbonate. The sodium bicarbonate, like you would take bicarbonate soda, you have an acidy stomach, that's what it does. The bicarbonate buffers the hydrochloric acid from the stomach. Remember, in the stomach, you have gastric juices. The gastric juices has a very, very low pH. You know, and this is something else that you'll get into in physiology. Talk about pH scales and acids and bases and all that kind of stuff. Well, pH scale measures acids and bases on the scale from 0 to 14, with 7 in the middle. And 7 is neutral. But if you're between 0 and 7, it's acidic. If it's between 7 and 14, it's alkaline. All right? Well, the gastric juices employs concentrated hydrochloric acid, which means that it's very, very, very acidic, has very, very, very low pH. The acid in your stomach has a pH of about 2. I mean, you can clean concrete with stomach acid. You know, it's like muriatic acid. Well, if you think about it, that's what's entering right here. Remember, that's at this point right here is the pyloric sphincter, and it opens up and it allows that chyme to enter. But what that chyme is, makes it all liquidy and creamy, is that hydrochloric acid. Well, what's going on in the small intestine? Remember, the small intestine, you're going to absorb that into the blood, but you do not want to absorb concentrated hydrochloric acid into your bloodstream, do you? No. So that's where your duodenum comes in. Your duodenum is your body's like little wet chemistry lab, because of the secretions from the pancreas with they're alkaline. If they're alkaline, they have a pH between 7 and 14. So what happens when you take something that has a high pH and mix it with something with a low pH? It neutralizes it. So that's what's going on. So we're neutralizing the chyme, right, from the stomach, so it can be absorbed into the bloodstream. That's kind of another long story for a short explanation. But that's what's going on in the duodenum with the pancreas. All right. Speaking of the duodenum, let's talk about the small intestine. Here I tell you, nearly all chemical digestion and nutrient absorption occurs in the small intestine. The term small, quote small, applies to its diameter, not its length. It's the longest part of your GI tract. And actually, pound for pound, it is the most massive part of your gut, okay? And so, well, why do they call it small? Because it has a small diameter, okay? It's about an inch and a half, something like that. And where the large intestine is a much, larger diameter, but it's much shorter. It's only about, large intestine maybe 5-6 feet long. But the small intestine, if you took it out of somebody's body and stretch across the room for about 22 feet, 22 feet, something like that. So it's very long. But it's long like that because your chyme is traveling through it, and it gives it time to make contact with that mucosal lining, which is very vascularized, and it's where you got your capillaries. So you're trying to absorb all that stuff into your bloodstream that's been broken down. So you're getting it into your bloodstream, and then once it's in your bloodstream, it's going to go to the hepatic portal vein from the superior mesenteric vein, right? And it's on its way to the liver, so we can sift through those crude metabolites and get your useful stuff. Anyway, let's look at the structure of the small intestine. Here I tell you there are circular folds called, see this little thing? This is the inner lining of a small intestine. These are called plicae or plicae circularis. And villi, these are villi, and actually microvilli. Collectively, all these kind of folds of various types of the mucosal lining up close, and then even the cells themselves have little microvilli, but they're all there, the plicae, the villi, microvilli, all to increase the surface area of the small intestine to maximize the absorption of nutrients. So that's the whole idea. So it's really long, but even in the lumen of the small intestine, there's further surface area for absorption to take place. That's what it's all about, is to get everything absorbed. All right. Now, it's very long, right? And it's broken up into 3 distinct regions. So we have 3 divisions of the small intestine. And you probably should have guessed that. Remember, there's always 3. What are they? Well, we already talked about the first one in passing a few times, the duodenum, not duodenum, for Dr. Cordes' students. I'm gonna get in trouble. Are you making fun of me? Shut up, lizard boy. Did he tell you stories about lizards yet? Yeah. Oh, you can't get away. Well, you know, he tells lizard stories, and I tell frog stories or other kind of. Everybody has a thing. You know, he's the lizard guy, I'm the frog guy, or whatever. Anyway, it's duodenum. All right. The word duodenum literally means 12 fingers. How many fingers do you have? You have 10 fingers, right? You got 10 fingers plus 2 more is 12. And why? What's going on? Well, I don't know. To tell you the truth, I'm just guessing here because long time ago, people used to measure things with body parts, you know, like feet. You know, I'm 6 feet tall, right? Because a foot was a unit of measurement. Even hands. I mean, we used to measure horses with hands. You know, so many hands high. A horse is like 15 hands high. And even fingers. Fingers were a unit of measurement. Duodenum, 12 fingers long. Now, it wasn't really this part of the small intestine. They measure 12 fingers, which is about 10 inches, and then just stop. I guess on average, that's how long it was, is from here to here. But beyond just calling it the 10-inch long or 12-finger long portion, it actually has boundaries, and I kind of define it for you. So here, okay, the duodenum, it receives the stomach contents. We know that through the pyloric sphincter, right? It receives the contents and the pancreatic juice and the bile. The stomach acid is neutralized here via the pancreatic juice and the secretions from the duodenal or Brunner's glands. And so look at this. This is a good illustration I hijacked from somewhere, but it shows you the 1, 2, 3 different parts of the small intestine histologically. And you can tell, really, this is the only, well, you can pick out this part of the small intestine. It's probably the easiest part to pick out, the duodenum, the initial segment, which is the shortest part. It's only about not even a foot, 10 inches long, or 12 fingers. It extends from the pyloric sphincter to this little, I didn't tell you about that. I thought I did somewhere. But it extends from here to here. I don't, maybe it's in a different lecture I'm thinking about. But anyway, it's not written, so listen closely or write it down. It extends from the pyloric sphincter, which would be right here, all the way to here to where it bends. Very, very distinct anatomical bend right here. It's called the duodenal jejunal flexure. That's the limits of the duodenum. That's this concave portion that forms. So often describe the duodenum as it looks like a C. And that C, the concave portion of that C, is to accommodate the head of the pancreas. The head of the pancreas fits in that concave port. Duodenal jejunal means duodenum, jejunum. The jejunum is the second portion of the small intestine. And that's what's going to take over here. But that's a very distinct feature. Now, under the microscope, you can see in the submucosa these duodenal glands, or the eponym is Brunner's glands. And these Brunner's glands only exist in the duodenum, because in the duodenum you have, well, that's where the acid that needs to be neutralized occurs. And so that's what these secretions from the duodenal glands are doing. They're producing their alkaline secretion to help neutralize that, in addition to secretions from the pancreas. So there you go. Now, what comes next? Well, from the duodenal-jejunal flexure, you have the jejunum, which extends for about 8 feet. Okay, so that's quite a ride there. I tell you, it's the middle portion of the small intestine that extends for approximately 2.5 meters, which is about 8 feet. You can tell or recognize the jejunum from the duodenum because at this point in the submucosa, there are no duodenal glands. So once the duodenal glands start to disappear, that's how you know that you're in the jejunum. That's like looking at sections of the small intestine all along the way. You know, if you take sections through here, you're going to find duodenal glands. And then you start taking sections from here, they start to disappear. And so for 8 feet or so, there's nothing basically in the submucosa, okay? Because at this point, I tell you right here, the chyme that had passed through the duodenum is neutralized. And so you don't need any more alkaline secretions. So that's that. Once, after about 8 feet or so, things start changing. That's where you enter into the ileum. Now here, you can't really see, you know, where the jejunum stops and ileum picks up. Not gross anatomical view, but under the microscope, you could. Once you, after about 8 feet or so, you're going to start to see something appear in the submucosa. In the submucosa, you have these lymphoid tissues that occur in the submucosa, and that kind of identifies the ileum, and that'll be for the rest of the length of the ileum. So here I tell you, ileum, which means literally twisted. Now there's 2 ilia. There's ileum, which is the small intestine, and there's ileum, which is your hip bone. Don't confuse the two. But this one is the distal portion of the small intestine. It forms the last 3.6 meters, which is about 12 feet. It comes to an end at the ileocecal junction, right there where it connects to the large intestine. Now, histologically, it has an increased number of goblet cells in the mucosa, and that, again, like I said, that lymphoid tissue in the submucosa, which is identified as either, you know, lymph tissue or Peyer's patches. Peyer's patches is the lymphoid tissue in the submucosa of the ileum. And of course, lymph tissue, like your lymphatic system, it's kind of like your adenoids or your tonsils or any lymph nodes. They're there to fight infection. So if you got some kind of bacterial something or another going on here that's out of control, well, you got the Peyer's patches to kind of keep things in check for you. Okay, here's the mucosa of the small intestine, looking up close at what's going on here. The villi, these little finger-like projections that are sticking up in there, those are the villi. Singular would be a villus, one villus. But collectively, they're finger-like projections of the intestinal mucosa, which maximize the absorptive surface area. That's why they're there. Their longest, the longest villi are in the duodenum, and then the villi become progressively smaller and shorter the further downstream you go. The more distally you head, they get smaller and smaller and smaller because you don't need them, because most of the absorption occurs in the beginning, or the proximal portion of the small intestine. But distally, you know, pretty much everything's absorbed, so you don't need that much more villi. The villi are covered with 2 kinds of epithelial cells. You got the columnar absorptive cells, so doing most of the absorption, and then the mucus producing goblet cells. And you kind of see that here. Here's the epithelial lining. The little pink cells, those are the normal columnar cells, which would be capped with microvilli, which kind of look like this. They coming up and down. And then the little blue, every once in a while cells you see, those are the mucus producing goblet cells. Then you look at this inside of each villus, the core. So the core of the villus is filled with areolar tissue containing a capillary network. There's an arteriole, a venule, and a lymphatic capillary called a lacteal. It's a green one, that's the lacteal. The lacteal is for the absorption of emulsified fats. All the other nutrients get absorbed into the circulatory system, but the larger globular things that were broken up by the bile are too big for the blood, so they're picked up by the lymphatic circulation, so they end up in the lymph, okay? The milky fluid produced by the digestive fats is called chyle. You had chyme and you had chyle. Don't mix up the two. Chyle is what you call the absorbed fats in the lacteals, okay? So, and then once it's in the lymphatic circulation, the chyle is conveyed from the lacteals to larger lymphatic vessels, and then from the lymphatics, the chyle is eventually transferred to the venous circulation at the right and left subclavian veins. So you file all these green ones back up, and they tap into the right and left subclavian veins. And so eventually that emulsified fat ends up into your circulatory system. And so, and then of course, your body uses it, all right? And you can see this. If you ever taken blood from somebody, or either just blood samples, or particularly if it's like a whole unit of blood, like in a blood bank, let the blood sit there a while. You can tell if that person ate something before they donated blood, an hour or so before they donated. And you can tell how greasy the food was, because it's kind of creepy. It looks like Crisco. It's like, oh God, that's in my blood. Yeah, it's because it'll separate out, and it's just like Crisco is going through your bloodstream, and it kind of makes sense how you can develop plaque in your blood vessels and so forth. Anyway, all right. So much for the small intestine. Let's move on to the large intestine. Divisions of the large intestine, we divide it up just like we divide up the small intestine. The large intestine begins, well, here I tell you it begins at the cecum. Now look, see how I spelled cecum, C-A-C-U-M, and then look down here, C-E-C-U-M. This is the old spelling. This is, I guess, more contemporary spelling. I guess this is the European spelling, and this is the American spelling, I guess. Oh, they dropped the A. But either way, the word cecum means blind, because the cecum is a blind pouch. It means blood. It's also called or described as a cul-de-sac, C-U-L-D-E-S-A-C, cul-de-sac, which is, I've learned, is French, which means bottom of the bag. Like if you have a bag, like a feed bag, and you reach down and there's like, you're reaching down in a sack and there's nothing in there, like the bottom, there's nothing there. That's the cecum, the cul-de-sac of the large intestine. It's nothing really there other than this, the vermiform appendix. Now, technically, this is where the large intestine begins. Although up here I say it begins at the cecum, but I guess the most significant part is the cecum. But the vermiform appendix is a vestigial extension of the cecum that we don't use. With vestigial, the human body is riddled with all kinds of vestigial organs and structures, which you don't use. That's what makes them vestiges. It's your ancestors used them, your non-human ancestors. Because at some point in our evolutionary history, our non-human ancestors utilized this portion of their gut. And those individuals had more of a herbaceous diet. Because you see this in animal guts. The more herbaceous they are, the more extensive their gut is. And if they rely more on animal proteins, they're more carnivorous. You don't need all that extra gut. So that's the typical rule of thumb. The meat eaters have a small intestines, the plant eaters have large, very complicated intestines. Okay. Well, humans, we're neither. We're kind of in the middle. So the complexity of our digestive tract is kind of intermediate. Not real extensive. It's not real short. It's kind of in the middle. And so we don't need all this extra gut, and so it's kind of atrophies and just kind of ends up as this little vestige. And that's what your vermiform means, worm-like. Most people just call it the appendix. This is the part that you have removed during an appendectomy. If you have an appendicitis, that's what we're talking about. It's anywhere from 4 to 6 inches long, hanging off the cecum right there, okay? So there's basically where your large intestine begins. I'm trying to advance, there we go. And then from here, all right, food would go up, ascend, straight up by the ascending colon. The ascending colon begins right here, I guess, right at the level of the ileocecal valve, passes up the right side of the abdominal cavity near the right lobe of the liver, where it becomes the transverse colon. So the right lobe of the liver right about here, it kind of makes a bend right there. Some books will actually define this little bend as the right colic flexure. Either way, it doesn't matter. But from there, it's the transverse colon, okay? It passes horizontally across the upper abdominal cavity and turns 90 degrees downwards. Right? And it goes down, descends, the descending colon. Ascending, transverse, descending on the left side of the body. So it goes down, 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 down. And it's anterior. It's in the front of your abdominal body cavity. All right, that's important because right about here in the anterior abdominal cavity on the left side, the colon turns medially and downward, forming a roughly S-shaped portion called the sigmoid colon. So this is you're going from the front, kind of zigzagging sigmoid towards the back. That's the sigmoid colon right here. This is usually the portion of the colon that people have most issues with when you're talking about like diverticulitis or something like that. And if you have to have a colon resection, this is usually the part that's not everything is perfect about the human form. Things could have been done a little bit better. And this is one thing because the arrangement of this colon creates trouble, so a lot of times it's got to be removed when people have issues with this. Anyway, but here it is. It goes from the front towards the back, and it's headed right towards the center, about where the sacrum is located. And here I tell you, within the pelvic cavity, the sigmoid colon straightens out and becomes the rectum. It kind of like makes a bank shot off the sacrum in the back and goes straight down. That's what rectum means. It means straight. So the straightened out portion in the back is kind of hugging the sacrum. That's your rectum, okay? The rectum structurally has 3 internal folds called rectal valves. You can see the last one right here, which enable the rectum, to retain feces while passing gas. So this is your function. The function of the rectum, basically, is to form stool. It's the turd forming portion of your large intestine, because at this point, the material that's traveling through the large intestine, all the digestion for the most part is finished. And so what you're trying to do is recover most of the water. So it's becoming dehydrated, but there you have normal gut flora, what they call coliforms, living in there. And they break down stuff, and a byproduct that they produce are gases, a lot of methane gas. And so you got a mixture of gas and dried stool. And so these valves kind of compress it. And so you got pockets of gas, pockets of stool. So you got a nice formed solid stool separated from your farts, basically, your flatus, okay? All right. Then the final, what I say, about 3 or so centimeters of the large intestine exists as the anal canal. So like basically from here to here. And usually in lab, where I talk about define the anal canal, is basically whatever's surrounded by the anal sphincters, okay? Here I tell you, it passes through the levator ani muscle and terminates as the anus. Here the mucosa forms longitudinal ridges called anal columns. You see these long columns with depressions between them called anal sinuses. And what they do is when the anus is closed and there's nothing passing through it, you got the sinuses that are intact, and they accumulate mucus. Okay, so little pockets of mucus. Right here, here you can see one sectioned open. See, you've got a little pocket of mucus here, a little pocket of mucus all the way around between the columns. And what it does, of course, the stool is dried compared to the rest of the stuff. So as the stool is passing through the anus, it kind of lubricates it. So it lubricates the stool, so facilitate the passing of your dried turd, so to speak. Okay. Then the anus. The anus is regulated by two sphincters. Remember, we talked about internal and external things, sphincters, where the internal is always, the deeper of the two is always the internal one, which is always smooth muscle. And the smooth muscle, remember, is governed by the autonomic nervous system. And just like in your bladder, you know, remember when the bladder's full, the smooth muscle relaxes, same kind of deal here. When the rectum is full of fecal material and it's like, okay, we got to go. You know, we got to go drop a load. Well, these internal sphincters will relax. And of course, it's not a good time. Thank goodness we have the external sphincters, the skeletal muscle. You can override that so you can hold it, you know, for as long as you can hold it. I was hearing on the radio how, you know, there's always an episode where somebody just couldn't hold it anymore. Accidents happen. So you got to like ditch your underwear. Got to leave your underwear somewhere because you had a little bobo, little accident. Okay, more anus talk. The anus is the, I define it. I guess I have to. The external orifice of the anal canal. Did y'all know that? Surrounding the surrounding external epithelium forms the anal verge. There's that word. I talked about this before in passing. What's the anal verge? I kind of like pointed out from here to here is the anal verge. What is that? This is hopefully where it all come make sense to you, come together. Your anal verge is analogous to your vermilion, your labial vermilion. So this part of your lips, you have an equivalent to it on the other end of your alimentary canal. So both ends are basically the same. This is the one coming in, your anal verge is the one coming out. Okay, because the histology is the same. Your labial vermilion, you don't have, it's not keratinized, and you don't have hair and integumentary glands there. It's different. But just beyond that, you do. And that's the same thing. The perianal area around there, it kind of takes over as normal keratinized integument, not in the anal verge, just like your labial vermilion. So that's kind of the deal. Here I tell you, it's the point where the non-keratinized stratified squamous epithelium of the anal canal becomes true keratinized skin marked by the presence of hair follicles and integumentary glands. That's where that kind of stuff takes over. All right. Then the mucosa. of the large intestine. The mucosa of the large intestine has simple columnar epithelium in all regions except the anal canal. Okay, it's where it is non-keratinized stratified squamous epithelium. That makes sense because you got stool going through there, and you got your anal columns and all that kind of stuff. You want a stratified epithelium there, not a simple columnar. The surface of the mucosa is rather flat in appearance in the large intestine. You see right there, you don't have villi sticking up. It's kind of like villi in reverse. There are no folds or villi, and rather you got these inverted villi we call intestinal crypts. Intestinal crypts, or the crypts of Lieberkuhn, is the eponym, same thing. They're abundant and deep compared to those in the small intestine. You have some in the small intestine, but they're all basically large intestine. Of course, you have goblet cells are most abundant in the intestinal crypts of the colon, of course. Again, more mucus to facilitate the passage of the developing stool. The end. So we are done with the digestive system. So you know what that means. We're going to start our last PowerPoint of the semester, which is the reproductive system somewhere. Where, let me go like this. There we go. PP. No, lucky 13. I didn't do this on purpose. It just kind of turned out that way. And just about every course, every textbook, every arrangement where you talk about body systems and it includes the reproductive system, they always put the reproductive system last. Do we save the best for last? Everybody likes the reproductive system, right? That's like save the best for last. Is that why we do that? Here I have reproductive system, anatomy of the sexes. We have sexes. Sexes are genders. And look at my first slide. You know, these are all William's original slides and creations and stuff. And I chose to do this for my first slide. This individual and this individual. In my mind, these two individuals would be the epitome of our human genders. Does anybody know what this is? What is this? Y'all know? Famous painting. It's called The Birth of Venus. And some people say, is that Mary? Oh, no. No. Yeah, are you think that the Blessed Mother would be portrayed like this? I don't think so. No. Actually, this is who Mary replaced. You know, way back in mythology, this was the Blessed Mother. Venus was the goddess of love and femininity and everything, you know, feminine. This is like the god of women, you know, basically. And this y'all know who this guy is? It's David. He's a sculptor. One of my brothers is actually a sculptor. And he went to, I guess this is in Rome. Is it in Rome? He studied this sculpture. And he told me all kinds of problems with it. Anyway, but he's considered, you know, very manly, you know, male form, so forth, are genders. Now, why is the best for last? Well, that's not why we do it last, really, because this system, it is a body system, but I kind of give you an overview of this system compared to all the other systems, and this is kind of why we put it last. Because I tell you right here, the first bullet in the second slide, the reproductive system is not necessary for individual survival, but for the survival of the species. So it's not about you. You yourself as an individual can live without the reproductive system. You know, You don't need it to live. You might not want to live. Oh no, I got to have my reproductive system. Well, not really, but it's not for you. It's for your legacy. It's for your species. It's so you can procreate your species. And so that's what it's there for. You know, you don't need to have all these organs that are in the system for day-to-day life. Although, like I said, you might not want to live life without it, you know. But anyway, what does it do? Well, here I tell you, the primary concern of the system is to produce and nourish offspring. Bam! It's not about you; it's about your kids, and everything about it is to ensure that that takes place. Okay, and I've said this before. You know, all individuals. Doesn't matter if you're a human or a goat or a coconut tree or some algae. All individuals are just vehicles for their genes. It's so that everything about the oak tree, everything about the algae, everything about the coconut tree or the kunas is about passing on their genes, all right? And to ensure that it exists long. And so you're really just vehicles for your dreams. So you kind of feel, I feel kind of used, you know, it's not about me. It's just my greedy gametes and my genes is because that they want to live on forever. And that's how life works. And that's what life's all about. So back to the anatomy. The system consists of course, primary and secondary sex organs. We always have this primary, secondary. Remember these two levels of a hierarchy, you know? You think primary, you think first, foremost, most important. And the secondary, important, but not quite as much, okay? The primary sex organs, the reproductive system, would be the gonads, okay? Why are gonads primary? Why are they at that level of primary? Well, they are the ones that actually produce the sex cells, the gametes. Remember the gametes, the sex cells, remember sex, gender, you know, each gender makes its own cell, okay? And sorry, Bruce, it's going to be one or the other. You can't be both. Males make spermatozoa, females make ova. Males make sperm, females make eggs. That's it. And it's those eggs and the sperm, those gametes that create the new individual. And that's how you perpetuate life. That's primary. That's most important. So the gamete and the gonad is primary. Okay. Everything else is not about making the new individual would be, you know, second fiddle. Okay, so that's what I tell you about. The secondary sex organs are all those. They're essential for reproduction. It's like the ducts and the glands and the penis and the male and the uterus and the uterine tubes and the female and the vagina. All that's secondary. Okay, see anything else you can think of the reproductive system be secondary. Now, there are primary and secondary sex characteristics. Don't confuse primary and secondary organs with primary and secondary sex characteristics. Primary sex characteristics would be simply just the presence of the primary organs. Now, if you look at an individual, a primary characteristic would be, oh, well, he has gonads. I mean, he has testes. If he has testes, he's a male. This individual has ovaries, she's a female. That's primary. But what's secondary? Secondary sex characteristics are the features that are not essential for reproduction, but are actually there to attract the sexes to one another, that makes something identifiable as one sex or the other. And that's why they're there. If you have differences between the sexes, those differences exist to make something look male-like or female-like, and they exist because the opposite sex wants it, basically. It's called sexual selection. You know, if there was a characteristic that none of the individuals adored or liked, you know, that the individual that possessed those characteristics, well, probably wouldn't obtain as many mates as an individual that possessed characteristics that everybody liked. And so that's the idea behind sexual selection, that characteristics are bred into existence because the opposite gender approves of it. I mean, that's how all things, at least that's how we look at it in biology, is that how all sexually dimorphic organisms come into being is through sexual selection. So, and if you have differences in the genders, that's why. Like, can you tell a male peacock from a female peacock? I guess it's a peahen and a peacock. What's the difference between a male and a female when you look at peacocks? You know? Have no idea. You know what a peacock is? You don't know. You know what a peacock is? It's a bird. Yeah.
Is that the one that talks?
Is the one that talks? Well, gosh, the ones with the nice feathers. Yes. Look, I've never done this before, but I'm gonna do it today just for you guys. Look, I'm going out on the internet. This could be dangerous. Typing in peacock. Oh, wish me luck. Ta-da! You see this? That's a male peacock. Isn't he pretty? That's a male peacock. I ought to save that image on my computer. Save picture as, whatever. Now watch. Peahen. It might be female peacock or peahen. There we go. No, here she is. She's not too cute. Yes, this is a female. That's right. Okay. She should be the prettiest one, she says. Yeah, look there. That's the girl. And then the boys, not so much. Yeah, they're the real pretty ones. So this is called sexual dimorphism, where you have differences between the sexes. The obvious difference is the males have the real pretty, ornate feathers. Let me go back to peacock. Okay. And look how beautiful. Look at this. Isn't it a gorgeous animal? Okay. Come here, you. Look. You know why he has feathers like that? And he's all strutting around like a peacock. Why is he doing that? To scare predators? Maybe because that's a viable, hey, that's a good hypothesis. But I give you a hint. He only shows off these feathers at a certain time, and it's when somebody's around. Who's around to see this? The peahen. Yeah, he does this to get laid. And you know what? It works, because females will judge the male. And they'll look at him and they go, yeah, that's okay, but I've seen better. And so it's only the best peacocks with the prettiest feathers and the most ornate decorations that the females like. And so guess who gets to get bred? The females will breed only with the males with the best feathers. And guess what happens to that male's genes? They get passed on through her eggs. And so his children and his children's children and so forth and so on inherit his ornate feathers. And if there's some kind of adjustment that takes place that's a little bit better, well, there you go. It just keeps growing and gets better and better as long as the female enjoys it and likes it. She, that's who it's her choice. That's, female choice. But there's such thing as male choice, female choice. It depends on the species. And so this sexual dimorphism is due to sexual selection. The female does that. And there's all kinds of things. Any difference you see in the male form versus the female form is due to sexual selection. Like for example, do you see many females that look like me? I'm a human, right? I'm a male and I've got this on my face. My wife doesn't have this. You know what? If my wife had this, we wouldn't have children. And no, that is exactly how the human female ended up to be hairless, because that's a male selection. Male selected for a more naked female, hairless female. It's a human thing. Most guys, most human males, doesn't matter from what part of the planet you're on, most males like a woman without a beard. Wouldn't you agree? Yeah, and then there's other things, So anyway, those are all secondary sexual characteristics, So that's kind of a roundabout way about something. Anyway, I got to get back to my lecture. Where do I go? Right here. All right, let me start my PowerPoint again. That was kind of fun. I'm kind of like, but you got to be careful going out on the internet like that. I don't want to, and this is all recorded. I don't want to record something bad. Okay. So that's all that. All right. Now, how do we make a girl and a boy? This is sexual determination and development. Beginning with, talking about the anatomy, the external, the development of the external genitalia in the fetus. All right. If you think about it, it's pretty easy to understand that, it doesn't matter if you're a male or a female. Remember we talked about the early cleavage stages? You had everybody's a zygote, right? And then there's the 2-cell stage, 4-cell stage, 8, and then the morula and the blastocyst. You can't tell a boy from a girl. It's too early. So when can you tell it's going to be a boy or a girl? Well, we've worked that out. And so that's what I'm talking about right here. Both sexes look identical until a certain point, okay? So here I tell you, in the fetus, the external genitals begin to form from identical structures in both sexes at about 8 weeks. All right, about 8 weeks around here, you have what's called a phallus. Both sexes have this. The phallus, you have urogenital folds, and then you have labial scrotal folds. Boy, girl, doesn't matter. It's kind of looks like a male, kind of like a female, but you can't really tell. Too early, 8 weeks. 9 weeks, the fetus begins to show sexual differentiation. Right here, when the male and female genitalia are fully formed by the end of week 12, where you have the male and female organs develop from the same embryonic origins are called homologous structures. So if you look, everything's color-coded, everything that's colored, the same color would be homologous. Thus, the penis is homologous to the clitoris and the scrotum is homologous to the labia majora and so forth. See how that works? So these are homologous, 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 right? See, and we'll talk about all that. In the male development, in the embryo, a cord of muscle and connective tissue called the gubernaculum, this green band right there, that's the gubernaculum. It's about 7 weeks. It extends from the floor of the scrotum, developing scrotum down here, all the way up to the gonad. Because in both sexes, the gonad is basically in the same position. The female will be an ovary, and male's a testicle. But we all know that the testes are on the outside of the body. But how do they get there? Well, that's what the gubernaculum does. It shortens as the fetus grows and guides the testis through a passageway in the groin called the inguinal canal. So that's this passageway, is the inguinal canal. The descent of the testes begins in weeks 6 to 10. And by about 28 weeks, the testis is actually in the scrotum. All right. Why? Why do we do this? Is a mammalian thing. Only mammals do this. So only mammals have a scrotum. You know, birds don't have a scrotum. You know, fish don't have a scrotum. Only mammals have a scrotum, and they keep their testicles not in the pelvic cavity, but out here just underneath the skin, out here dangling in the breeze. That's exactly why it is, to keep them cooler. In humans, the testes are kept about 3 degrees cooler, centigrade that is, than the pelvic temperature. The pelvic temperature is about 37 degrees, so about 34 degrees-ish is they kept a little bit cooler. A little bit too warm, that's, you don't have normal spermatogenesis. The sperm formation will not take place. So you can sterilize a male. If you kept his testicles up in his body cavity, he would not produce sperm. Look at this. This is a newborn. Look, brand new, still umbilical cord, still attached. All right, here's the scrotum. Here's his uncircumcised penis, and I'm drawing a circle around here. This is a bulge right there. Right there. I'll tell you about 3% of males are born with one or both testes undescended. So they're supposed to be pulled to the outside. You see his right side of the scrotum is nice and full, but the left side, it kind of looks deflated because his left testicle is still stuck in the inguinal canal. It's a condition called cryptocoidism. It can be bilateral or unilateral. This is unilateral cryptocoidism right here in this individual. It can be, you could, sometimes it'll descend on its own, but in many cases it has to be corrected with surgery. One of the first surgeries a former student of mine did, he's a veterinarian now, but he was so proud of it, and it was pretty exciting. And he sent me pictures, and it was to correct the cryptocoidism in a horse. Yeah, he had a horse just like this, and he showed me pictures, and it was funny because, you know, you don't think of a horse being on an operating table, but they got operating tables for horses. And there's a horse, you know, under anesthetic with his hind legs way up in the air, you know, and he showed me pictures of him, you know, correcting this surgery. It's a thing, but anyway. Let's stop there. We'll save this for next week, and then we'll probably finish this up or get close to it. But I don't want to, I need a little bit more time to finish the female development. But we'll do that Tuesday. So you guys have a good weekend, and we'll wrap it up next week. Okay. See y'all then.